This is muscle video number 10, and this is going to be the first video of 2 where we cover the action potentials. And when you look at an action potential, well, actually, before that, if you look at our learning objectives here, define sodium equilibrium potential, potassium equilibrium potential, and then 2 more, your ability to do this, your ability to reach these learning objectives really hinges upon your confidence level with this whole thing that we've covered in previous videos. You should be very comfortable with the idea that sodium is primarily extracellular and wants to go in, and potassium is primarily intracellular and wants to go out. In addition, you should be comfortable with the concept of equilibrium. If you're not, then I'd encourage you to go back and watch those sections again, read about it in your textbook, because this idea of equilibrium is very, very important. So as we go into these learning objectives, let's first do sodium equilibrium potential. Now, the first thing that you already know is that sodium is primarily in an extracellular environment, and it lives out here. The one thing that I do want to tell you is that resting memory potential is negative 70 millivolts. You just need to accept that when sodium and potassium are kind of doing their thing, and most of the doors are closed, or all the doors are closed, except for a little bit of sodium, potassium that can always kind of leak through. In some ways, you can imagine your home, when you've got all the windows closed, all the doors closed, there's still a little bit of air that leaks through, just through the little seams around the door, the little seams around the window. So there's always going to be a little bit of air exchange with the outside. Similarly, there's always going to be just a wee bit of sodium leaking through. There's always going to be a little bit of potassium leaking through as well too. But outside of that, when all the main doors are closed, the doors and windows are all closed, what we'll see then is this type of situation where the cell is resting at negative 70 millivolts. Now, what I'm about to do here, just consider this picture, ignore this one over here for the time being. If you just look at this picture, most of my sodium is on the outside. Which way does sodium want to go? It wants to go from out to in. Can it do it without a door? No, of course not. You need to have a door there. So now in the next scene, what I want you to imagine is that I want you to imagine that the doors themselves open. And when sodium doors open, which way does sodium want to go? It wants to go from out to in. What I want you to see then is that as sodium comes in, you're going to make that cell less and less negative. So I want you to imagine this. Let's say 1 sodium comes in, and this negative 70, what will happen to it? Will it get less negative or more negative? Considering sodium has a positive charge. It's got a positive charge, so the thing's going to get less negative. And so what I want you to see is that as you let more and more sodium come in, sodium will eventually come in to the point where it reaches equilibrium, where the chemical balance and the electrical balance is just at that same point, at that right point where the amount of sodium going in is the same as the amount of sodium coming out. Again, net movement in is the same as net movement out. That is sodium equilibrium. Now, when that happens, the measurement inside the cell, the measurement of the electrical potential is now actually plus 35. It's positive 35 millivolts. So the key thing that I want you to know here is 2 things. Number 1, when sodium is allowed to come in to the point of reaching equilibrium, you leave the doors open until sodium reaches equilibrium. When that happens, the measurement of the cell on the inside is now positive 35 millivolts. The other thing that I want you to note here, and this goes back to that last video, what we do not see is equal amounts of sodium on the inside and the outside of the cell. Right? That is not equilibrium. It does not mean we have equal concentrations. And in fact, when sodium reaches equilibrium, you'll see we actually still have a huge gradient set up on the outside. We still have a ton of sodium on the outside and just a little bit on the inside, yet I am at equilibrium at this point because the net movement out is the same as the net movement in. So when we look at sodium equilibrium potential, what is sodium equilibrium potential? It's the potential, which is the electrical measurement. It's the electrical measurement of the cell when sodium has reached equilibrium. And what is that number? That number is plus 35, positive 35 millivolts. And again, that makes sense because we're taking positive charges from the outside and bringing them to the inside, taking what was negative and making it less and less negative. Okay, so really what that means, look, this is just a gross image where I'm just using big bubbles for sodium, but really what that means, if you can imagine 1,000,000 sodium out here and like 5 on the inside. When 1 sodium comes in, it's negative 69. Another sodium comes in, it's negative 68. Another sodium comes in, it's negative 67. A bunch more sodium comes in, now I'm at negative 20. A bunch more comes in, now I'm at negative 1. A bunch more comes in, now I'm at positive 5. A bunch more comes in, now I'm at plus 35. So the reality is, yeah, there's a bunch of sodium comes in. But in the big picture, if I've got 1,000,000 out here and 5 on the inside, by the time I've reached equilibrium, I now have, instead of 1,000,000, I've got 999,900, and I've got 100 on the inside. So meaning I've still got a huge gradient set up, even though I'm at equilibrium. That's the key point here. Now, that absolutely must make sense to you. This idea of equilibrium and the measurement on the inside of the cell, that must make sense to you. If it doesn't, for now, then I'm okay with you memorizing it. As long as you memorize the fact that sodium will go from out to in, and because he's positively charged, you'll make the inside of the cell less and less negative. And when sodium reaches equilibrium, you're at plus 35 millivolt. Now, let's do the same thing with potassium. When you look at potassium, potassium is primarily on the inside of the cell. What was our number again? It was at negative 70. That was resting membrane potential, right? That's when all the doors and windows are closed. Potassium can't get out, except through these little leaky pores, these leak channels, just like a little bit of air squeaking in through the sides of your windows, even though they're closed. So now, what happens is now I'm going to open up potassium doors. And now when I open up potassium doors, which way does potassium go? Potassium moves down his electrochemical gradient going from in to out. So here he goes going from in to out. Now imagine this again, 1,000,000 potassiums on the inside and 10 on the outside. Okay, just imagine that. Now a little bit of potassium goes out. What happens to the charge here? Well, I've taken positive charges and I've pushed them to the outside, which means my negative environment will get more and more negative. So if I say, for example, negative 70 minus a positive charge, then what you'll see is negative 71. Another potassium leaves, and now it's negative 72. Another potassium leaves, now it's negative 73. Another one leaves, or a handful leave, I'm at negative 80, so on and so forth. Now, a bunch of potassium leaves. How much leaves? Until I reach equilibrium. And so once I reach equilibrium, now what you'll see is, again, I still have a bunch of potassiums on the inside. So remember, it's not equal concentrations. So at this point, if I had 1,000,000 here and 10 here, now I've got, again, 999,900 on the inside and then 100 on the outside. So yes, a bunch did leave, but I still have a very, very steep concentration difference here. So now, potassium doors are open, that's what happens. And what's my measurement? I'm now at negative 90 millivolts. So these two slides, this idea of what happens to sodium once I open sodium doors, sodium reaches equilibrium, and the measurement is plus 35. Once I open potassium doors, potassium leaves, it reaches equilibrium, and the measurement now is negative 90. Again, both of those, they started at rest, which was negative 70 millivolts. Now, let's add in a couple more vocabulary words. The process, remember the cell is resting at negative 70 millivolts. Depolarization, that word depolarization is the process of making the inside of the cell less negative. So everything that I showed you here, when sodium moves, what I'm doing here is I'm making the cell less and less negative. The fancy name for that is I am depolarizing that cell membrane. I am depolarizing the cell membrane. On the other hand, when I make the cell more and more negative, like I showed you here in that previous slide, I'm making the cell more and more negative. That term is hyperpolarization. I'm making it more and more polar, so to speak. So I've depolarized and I've hyperpolarized in this situation. Okay. Now, what I'm doing here, when I make it more and more negative, I only use the word hyperpolarization when I start off at negative 70. But what I'm going to show you in a future video is that if I go from negative 70 all the way up to plus 35, negative 70 to plus 35, and now all I want to do is that I'm now just going to rebound, and meaning I'm just going to go back to the way things were. This is at a later time point. Stuff happens where my plus 35 then ends up coming back to negative 70. That process is actually called repolarization. And we'll use that word a lot more as we continue on understanding the action potential. Okay, so here's where we're at. We know sodium equilibrium potential. We know potassium equilibrium potential. We know what depolarization, hyperpolarization mean. Now, let's get into this idea of a sodium-potassium pump. What the heck is that? Well, listen, remember I told you that sodium goes down as gradient, potassium goes down as gradient. And so I made up those numbers. I said 1,000,000 on the outside, 10 on the inside. And here it becomes 999,900 on the outside and 100 on the inside, right? So imagine I do it again, and then again, and then again, and again, and again, and again, and again. I mean, let's say I just do this like 100,000 times. You can imagine that eventually I might deplete this gradient. What I mean by that, eventually I might have, 600,000 out here, 400,000 on the inside. And then I do it a bunch more. And now I have 550,000 out here and whatever. I can't keep the math straight. 500,000 out here. My point is, if I keep going forever, and okay, not exactly forever, but if I keep going, eventually, over time, I will get to the situation where I have equal concentrations on the inside and the outside. And again, that's going to be really, really bad. I don't want that to occur. I don't want equal concentrations on the inside and the outside, because at that point, my cell is no longer electrically excitable. There's no more gradient set up. So I never want that to happen. So how do I reconcile that? Well, I want you to imagine this. If you ever seen one of these indoor, well, this happens to be outdoor, but one of these like homemade waterfalls, then imagine water at the top. I just let it loose and eventually water trickles its way down. Look, and maybe it's a ton of water. Maybe I've got a 100-gallon tank up here, and then this thing trickles downstream for hours and hours, maybe days on days, and maybe weeks. But eventually, that bucket of water is going to be completely emptied and depleted. So then what ends up happening, there's no more gradient, right? There's no more high water compared to low water, so therefore there is no more waterfall. Well, liken that to what's happening here. This is a waterfall of sodium going downstream. This is also a waterfall of potassium going downstream. It's still downstream in the sense that high to low concentration. Well, again, left to its own devices, that gradient will ultimately disappear. So what do? We have a pump here. And that pump is set up where it's going to constantly pump water upstream. So you have a never-ending reservoir of water here, so it can continue to trickle. So as long as you got power to this thing, that waterfall will continue on literally forever, as long as the power is running and the water's in there, okay? Because I'm constantly pumping water upstream. Now, I can't pump more than comes down, right? I can't do that because otherwise this pond will be completely empty. But my point is I'm constantly pumping in the background. Kind of these pipes are usually buried somewhere. These pumps are usually hidden and tucked away somewhere. And so these things are in the background, always constantly going, so that this gradient, high water to low water, never disappears. So water flows down its gradient. This thing, why does this thing pump water? Which way does it pump water? It pumps it against its gradient. Well, that's what we need to do. Sodium comes in. We need to have a system where we're constantly pumping sodium back upstream. Potassium goes out. We need a system where we're constantly pumping potassium back upstream, so to speak. And you guys have seen stuff like this in the electron transport chain, for example. And so what that thing is here, it's a sodium-potassium pump. The sodium-potassium pump will constantly and forever pump 3 sodiums against its gradient and pump 2 potassiums against its gradient. It burns ATP in doing that, but what that ensures a situation where we always have something like this, where most of the sodium is on the outside and most of the potassium is on the inside. So even though sodium leaks in, if we just let it leak in without ever pumping it out, then eventually you're going to have equal concentrations. We can't let that occur. So it leaks in, and we always have a pump working quietly, pumping sodium back out. And the same thing with potassium. Okay, so that's the idea of the sodium-potassium pump. 3 sodiums go out for every 2 potassiums go in. So this is just another look. There's my sodium channels with most of my sodium on the outside. There's my potassium channel with most of my potassium on the inside. You know which way sodium goes when the door is open. You know which way potassium goes when the door is open. And we have a sodium-potassium pump constantly pumping sodium back out and constantly pumping potassium back in. All right, so let's see. We've covered this learning objective, potassium equilibrium potential, depolarization, hyperpolarization, as well as that word repolarization. We introduced that term as well too, and we'll use that a lot more in the next video, as well as the role of the sodium-potassium pump. The next video is going to start looking at some of the, number one, how do we open those doors? And then once those doors open and things reach equilibrium, what does that look like? And that would be then our action potential.